Okay, folks, so now we're going to play the same game that we did with changes in internal energy. However, we're going to do that with changes in enthalpy, and we're going to look for physical observables that manifest from these derivatives and relationships that we create. So we'll play this same game. We're going to look at a closed system, so constant number of moles, but is free to exchange heat between system and surroundings. And now we're going to choose P and T. Okay, so we note that H is a function of T, V, and P. But just like we only picked two of those for U, we're only going to pick two for H. And hopefully we'll see why in a moment. So the partial of H then must be the following. So the total derivative in H must be the following. The partial in H with respect to the partial of P at constant T dP plus the partial of H with respect to the partial of T at constant P dt. And now once again, we'll look at these derivatives and try and see if we can't find some relationships that are familiar. And hopefully we can see this one, recognize it. That is Cp, the constant pressure heat capacity. So rewriting this expression now, we can say dH equals the partial of H with respect to the partial of P at constant T dP plus Cp dt. And so what I want to note also, right, don't forget our twins. Okay, so we looked at, in an adiabatic way, du at constant volume equals Cv dt. Well, the partial of H with respect to P equals Cp dt. So now we can see why we've already established that U seems to kind of want to naturally tend on T and V. And thus, H will naturally want to tend on T and P. Okay. So we've got the whole gamut of our changes with respect to either their internal energy or their enthalpy. So continuing along, if we want to look at this derivative now and ask, okay, what is this quantity? We've got to invoke a couple of situations to work through that. So the situation we'll assume is that we have an adiabatic container. Okay, so I know that this said closed, but now we're going to see, well, what happens if we make this adiabatic so that it can't exchange heat? And so what that means is we're looking at an isenthalpic situation. So dH equals 0. So now that's 0 on this side, which is the partial of H with respect to the partial of P at constant T dP plus dP, plus Cp dt. And now if we work through this, we can write the following. Negative Cp dt equals the partial of H with respect to the partial of P at constant T dP. And now so that we can hone in on this derivative, I'm going to divide both sides by dP. And then now we're going to say the following. That derivative, partial of H with respect to the partial of P at constant T equals negative Cp and the partial of T with respect to the partial of P at constant H. And so this right here is now a more useful derivative that we can attempt to measure. Changes in temperature with respect to changes in pressure at isenthalpic conditions. So that is much easier to measure than changes in enthalpy with respect to changes in pressure at constant temperature. And as it turns out, this gives us the definition of a known quantity. It's called the Joule-Thomson coefficient. Okay. Coefficient. And it has the Greek letter mu. And by definition, the limit of the partial of T with respect to P at constant H as P approaches 0 gives us this quantity, the Joule-Thomson coefficient, okay? And I will go, we'll have a whole video dedicated to just describing the Joule-Thomson coefficient coming up next. I'll see you then.